Welcome. In this video, I'm going to take a look at the new paper 3 for the 2016 SL Chemistry exam. So as you notice, there's two sections to paper 3 now, and instead of being two different options, section A will be some experimental data that you're asked to comment on or analyze, and then section B will be over the one option that you've studied. So a calculator is allowed, as well as the data booklet. The maximum marks are 35, 15 for part A and 20 for part B, and you have an hour to complete it. So question number 1, section A has two questions. You have to answer both questions and write your answers within the boxes provided, just like paper 2 of the other exam. So as you look at all this information, it may look similar to your ACT exam. As you take a look at it, there's a lot of information, but it talks about these refrigerants, use different classes of compounds, and then they have different levels of chlorine and fluorine on the carbons, and then they've got these ODP, GWP, enthalpy of vaporization, and atmospheric lifetime. And if you look down to the footnotes, it tells you that ODP, the ozone depletion, is a relative measure of the amount of degradation to the ozone layer caused by the compound compared to the same mass of CCl3F, which has an ODP of 1. And then GWP is a relative measure of the total contribution to global warming over a specified time. And the key here is that you notice both of them say they are relative measures. And so question 1 wants to know why there's no units for either ODP or GWP. And the reason why is because relative means it's compared to a standard. So both are what we call relative measures or compared to some standard. So it's like saying my grades are better than your grades. There's not a unit for it, it's a comparison. The rest of this question, you have to flip back and forth to the graph. I'll make reference to it, but you should be able to look at your own copy. But part 2 says, by making reference to the chemical formulas and the ODP values of the compounds, comment on the hypothesis that chlorine is responsible for ozone depletion. Well, what you should notice is that the ODP values is greatest for CFCs with 2 and 3 chlorine. And so ODP value does seem to go up, so the ODP value does increase with the number of chlorine. So yeah, the hypothesis seems to have some validity. It's much less for HFC that has no chlorine on it. And part B then, use the data from the table to interpret the relationship between the atmospheric lifetime of a gas and its GWP. And if you look at those two values, you should notice there's a direct relationship as GWP increases, so does the atmospheric lifetime. They increase and decrease together. So on part C, we have another graph here comparing the percent of either CO2 or CH2FCF3 remaining in the atmosphere compared to the years since it's been emitted. And part 1 simply wants you to name, use the IUPAC rules to state the name of CH2FCF3. Since we have 2 carbons, and it's all single bonds, here it's saturated, you could think of this as an ethane group. And there's 4 fluorine substituted on it, so it's going to be tetrafluoral ethane. And then I have to tell you where those fluorine are located, and it's 1, 2, 2, 2 tetrafluoral ethane. Or sometimes that's also called 1, 2, 2, 2 tetrafluoral carbon. The second question then says, the heat of vaporization for this compound is 217 kilojoules per kilogram. Calculate the value for 1 mole. Well, I have to convert kilojoules per kilogram to kilojoules per mole. So to do that, I need to find out how much 1 kilojoule is in moles. So 1,000 grams of this stuff, if I converted it to moles, would be 102.04 grams per mole, adding up all the pieces. So that would be 9.8 moles is what we're talking about when we're talking about 1 kilojoule. So if I know that 217 kilojoules per kilogram is released, I can now multiply by the 9.8 moles in a kilojoule. So I want moles on the bottom and the 1 kilojoule, or kilogram, I'm sorry, on top, so that this becomes kilojoules per mole. So I take the 217 divided by 9.8, and I come up with 22.14 kilojoules per mole. And since I've got the opposite process, this was heat of vaporization, and I'm switching it to condensation, this would become an exothermic process, or energy would be given up. So I'm going to include the negative sign as well. And then part 3, with reference to the graph on page 4, comment on the atmospheric lifetime of CO2 relative to the tetrafluorocarbon and on the likely influence of this on climate change. And what you should notice is that there's a lot more CO2 remaining in the atmosphere over the years versus the amount of the tetrafluorocarbon. The tetrafluorocarbon in the first 50 years drops down to almost zero, whereas the CO2 still stays at fairly high levels of about 30%. And even after 100 years, there's approximately 30% of CO2 still out there, while the CH2FCF3 is about 0% left. And so the CO2 emissions stick around and influences our climate. Which is the effects we're seeing now after all the years of inflating our CO2 levels. Then question number 2 talks about an experiment. Thomas wants to determine the empirical formula of a red-brown copper oxide, so we know it has copper and oxygen. He's going to convert a known amount of copper to sulfate. He makes 100 centimeters of 1 molar solution of copper sulfate. He reacts a known volume of the solution with alkaline glucose to convert it to red-brown copper oxide. Then he separates the precipitated oxide and finds its mass. So it says Thomas calculates that he needs 0.1 times the molar mass there of copper sulfate to make the solution. Outline the major error in his calculation. And his error is that it says it's a hydrated copper sulfate, and he hasn't taken into account the mole or mass of water. He's only using an anhydrous molar mass when he used a hydrated sample of copper sulfate. He now adds 100 centimeters cubed of water, dissolves the copper 2 sulfate crystals. A friend tells him that for making standard solutions, it is better to use a volumetric flask rather than adding water from a measuring cylinder. Suggests 2 reasons why a volumetric flask is better. And I know we haven't used volumetric flask in class, but basically it's a flask and it's got the mark right on it where your 250 would be at. And a couple of reasons why it's better is it's more precise, there's less uncertainty. Associated with it. And the other thing is you'd have your crystals and you would add the water to it till you're up to the 250 mark instead of putting the crystals into the flask and then measuring the 100 centimeters cubed separately and adding it to it. So it truly measures the total solution instead of just measuring the water added. Although the crystals aren't going to change that volume very much, but certainly it could have some effect on it. So So it's measuring the total volume of the solution, not just the solvent. Another one I would propose is that you don't have to transfer you can add your water directly in. Instead of measuring your amount and then transferring it, there's always some water left behind in any container. Part C says Thomas now heats 25 centimeters cubed of the solution with the excess alkaline glucose to convert it to a suspension of red-brown copper oxide. Describe how he can obtain the pure, dry, solid product. Well, he's going to need to do a couple things. Assuming that all of his reactant hasn't reacted, he needs to do some separating and then drying out of it. So first of all, he could filter or centrifuge to separate the solid. So it's going to separate his solid from his solution. Then he should rinse it with water to try and dissolve any impurities. And then he needs to dry it in the oven so that he only has the copper oxide crystals remaining. Part D, using the same chemical reaction, suggests how Thomas's method to determine the mass could be obtained from a known mass of copper 2 sulfate crystals might be simplified to produce more precise results. Instead of using a standardized solution, he could have just taken a known mass of copper sulfate and reacted it with the alkaline glucose. He doesn't have to put it in a standardized solution. So use a known mass. Instead of making a standardized solution. Question 13 then starts part B and starts the questions over your options. And question 13 says, salicylic acid has been used to relieve pain, blah, blah, blah. And they show you the structure for salicylic acid and acetylsalicylic acid, which is what we know as aspirin. It says, identify the type of reaction used to convert salicylic acid to acetylsalicylic acid. So what you should notice is that the OH group has been replaced with the COOH group. It happens to have a methyl group with it as well, but really what happened is this H was removed and this group took its place. And so that's what we call esterification. The reaction where an ester is made from an alcohol and a carboxylic acid. Or you could also call it condensation because it's going to remove an H2O. It's going to take the hydrogen from the alcohol as well as an OH group from the carboxylic acid. Part B, you've got some infrared spectra for salicylic acid and acetylsalicylic acid, and you're going to be asked a couple questions on the next page. So as you look at these two, you want to notice what they have in common and where their differences are. And there's definitely a lot in common on these, but a couple things that you might notice are a little bit different is I see some slight differences here and here. Looks a lot the same coming up here, but right here there's a second peak on the acetylsalicylic acid. This is very much in common, but there's an extra peak up there on the salicylic acid. So it's important to pay attention to where those peaks occur, at what wavelength, and it's also important to remember what compounds were in the structures. Remember, each structure has a benzene ring, some OH, and some carbon bonded to oxygen, both single and double bonds. So the questions on the next page, it says contrast the two spectra with respect to the bonds present, and this is worth 3 marks. So what you should have noticed is only the salicylic acid has a peak at around 3200, which would equal its extra OH group. would correspond to that frequency. The acetylsalicylic acid has 2 peaks at around 17 to 1800. And that would be for the 2 double bonded oxygens that it has. And then for the third mark, you should point out some things they have in common. Both have strong peaks around 1050 to 1400, which would be the CO group, or at the 2850 to 3000, they have a lot of similarities, which would correspond to the CH bonds they have in common. Part C says a modified version of aspirin is sometimes made by reactant with a strong base such as sodium hydroxide. Explain why this process can increase the bioavailability of the drug. And what you're supposed to realize is the sodium hydroxide produces what's known as soluble aspirin, or it's also known as an ionic salt. And what that means is it's going to be more soluble. The extra OH, which you're going to pick up from the NaOH, makes it more soluble in water. And more soluble in water means more in your bloodstream. And then off to the target areas. Question 14 talks about a couple of antiviral drugs used for influenza. Question A is a general one. Outline why viruses are generally more difficult to target with drugs than bacteria. One is because they lack any cell structure of their own. So it all depends on what host cell they end up in. A second problem is that they exist in a host cell. So you often have to kill a healthy cell to get at the virus, and you have to know what that healthy cell is. And a third reason, and you just needed one of these since it was 1 mark, is that they mutate quickly and frequently. So you kind of have a moving target and a changing target. Part B says, by reference to their molecular structures given in section 37 of the data booklet, state the formulas of 3 functional groups that are present in both of these antivirals, and the formulas of 2 functional groups that are present in the zanamivir only. So if you look up those structures, you should notice that it says the formulas, so not the names. There's an NH2 group for the amine. There's the CONH2 group. There's also a carbon double bond, an alkene group, and there's also an ether group. But they make sure you read carefully because they specifically asked for the formulas there. Present in zanamivir only is the OH and the COOH groups. Part C says, comment on how the widespread use of these drugs may lead to the spread of drug-resistant viruses. And just like with the drug-resistant antibiotics, anytime you use it, only the strong survive. So in this case, only the strong viruses survive. And that means only the strong reproduce, not the weak. And that's what develops resistance over time. Part D outlined the general processes that should be followed to promote green chemistry in the manufacture of drugs, such as these antivirals. 3 of the big issues with pharmaceutical drugs is, first of all, using solvents that are preferred. So using safe solvents, safe for the environment, safe for the workers. So using solvents that are on the preferred list. Reuse or recycle the waste to get maximum production. And use renewable resources where possible. So pretty much the same practices that you would want for green chemistry in any industry, or to be green in your life in general. Use safer products, reuse or recycle where possible. Question 15 asks you about antacids. And first question says, formulate an equation to show the action of the antacid magnesium hydroxide. So first of all, you have to know that magnesium hydroxide is going to be MgOH parentheses 2. Stomach acid is represented with HCl. So that's going to produce MgCl2 and H2O. And since I have 2 hydroxide, I'm going to have to balance with a 2 here and a 2 here. Then part B says an antacid tablet with a mass of 0.2 grams was added to 25 cc's of 0.125 molar hydrochloric acid. After the reaction was complete, the excess acid required 5 cc's of 0.2 molar sodium hydroxide to be neutralized to determine the neutralizing power. So what they don't tell you, which would be helpful, is what they mean by neutralizing power is they want to know how many moles of HCl do you neutralize per gram of antacid. That's why they're telling you the information that they are. So first of all, if I set up an equation, I have some antacid, so some metal X with OH, and it really doesn't matter if it's XOH2 or XOH3 because the molarity is going to work out the same. I have HCl combining with that to give me a salt and then the H2O. And again, I'm not going to use molar ratio, so I'm not going to be concerned about what metal I happen to be using here. I'm using 0.200 grams of this, which I'll need a little bit later. I'm using 0.025 liters from the 25 cc's, and it's a strength of 0.125 moles. So my first step is to find out how much HCl did I actually start with, because I know how much I had left over, at least how much NaOH it took. So if I take the 0.025 liters of HCl times the 0.125 moles per liter for the concentration, that lets me know I have 0.003125 moles of HCl that I started with. That's how much is in this amount up here. But when I got done, I took 5 cc's or 0.005 liters of NaOH with a strength of 0.200 moles per liter to neutralize the extra acid. So that means I use 0.001 moles of NaOH, which means it neutralized 0.001 moles of HCl left over. So this is what I started with, my initial amount. This is what's left. If I subtract these two and get 0.002125, that's how much HCl was used. So 0.200 grams of hydroxide neutralized 0.00125 moles of HCl. So I could take 0.00125 moles of HCl, divide by the 0.200 grams, and I have a neutralizing power of 0.011 moles neutralized per gram of antacid used.